So I remind you, we discussed a formula for the center of mass object, which we wrote as x of the center of mass is equal to x1 m1 plus x2 m2, so on and so forth, divided by the total mass. So we're using this formula today to solve this question. We have three uniform thin rods, each of length L equals 22 centimeters. They form an inverted U. The vertical rods each have a mass of 14 grams. Let's label these as M1 and M2. So M1 equals M2 equals 14 grams. And the horizontal rod has a mass of 42 grams. I'll label this as M3. What are the x coordinate and the y coordinate of the system's center of mass? So I'll need to use this formula and apply it along the y direction as well. One thing I should do next is I need to look at my systems. I have rods. X1, it's usually the position of one point, not a full rod, right? So what I have to do here is I'll take a look at the rods as they are and find the center of mass of each rod. Like this vertical rod is all uniform. So its center of mass is simply at its center. I will represent the rod to have this mass, which I can represent as a point M1 and will have coordinates x1. The horizontal rod, same story. It is bigger, but its center of mass will still be here. So this is M3. And the vertical rod on the other side, its center of mass is definitely over here as well because it is uniform. So these 3 points are the ones I will study. Even better, I'm gonna also locate them because we need to give them some x and y positions, right? I will choose my origin to be at M1. This makes my calculation easier. Now all I have to do is put some coordinates for M1, M2, and M3, and then I will plug these in my formula. Namely, if you look at M1, it has coordinates 0, 0 because I chose it to be at the origin. M2 has coordinates, well, this is x2, this whole thing, which is none other but the length of the third rod. Now, all rods have the same length of 22 centimeters. So x is 22 and M2 is on the x-axis, so it has no y coordinate. M3 is over here. So its x is actually halfway through the rod because this is the center of mass. So x3 is L over 2, which is going to be 11 centimeters. And this is y3 because I'm here, so it coincides with y-axis at this point, which is also half of the length of the rod. This is 11 centimeters.
Professor,
Yes.
وين حطيت السنتر اوف ماس؟
So
وين مكتوب XL ولا هذا شيء ثاني ما
So I don't know where the center of mass of the whole system is yet. I want to calculate it using the formula, but in the formula I have x1, m1, x2, m2. We use this formula for some given points. Like I would have this triangle and then x1 is the position of this point, x2 is the position of this point. Here I have rods. So what x do I locate, you know? So what I did was I found the center of mass of each rod alone, like this one, this is its center of mass. This rod, this is its center of mass. It's simply at the center of the rod because these are uniform rods. So now I end up with 3 rods. These are the centers of masses. I'll take the position of each center of mass. This is the system I have now. I'm going to study this system, which contains the center of mass of each of the rods. All right, and then the center of mass of the whole thing, of the whole arrangement of rods, well, it will be somewhere at the center of this triangle, right? So I can approximate where it is, because I ended up with this isosceles triangle. So the center of mass, well, the upper rod is heavier, so maybe it's somewhere here. Makes sense?
Yes, thank you, Professor.
Yeah, now I'm gonna apply the formula to make sure where the center of mass is. I found the locations of the center of masses for each rod, and then I'll apply these locations and the masses to the formula here to find the position of the center of mass of the whole arrangement of rods. So I have x1 is 0, x2 is 22 centimeters, m2 is 14, x3 is at 11 centimeters, and m3 is the horizontal rod, which is heavier. It has a mass 42. I'll divide this by the total mass, which is going to be 14 plus 14 plus 42. So I left the masses in grams because the units will really cancel out between the numerator and the denominator, so that's fine. I don't have to worry about the conversion. And I left x1 and x2 in centimeters because, well, I could just get the coordinates in centimeters for the whole arrangement as well. So the COM I will get will be also in centimeters. So I'm gonna just calculate this. I got 11 centimeters here. So x of the center of mass is at 11 centimeters over here. And this makes total sense. Guess why? If you check the physics, my arrangement here is symmetric. So, like the two rods, their centers of masses are here and here. And then the center of mass should be along the vertical line that contains M3. So the center of mass should be at the center, at the midpoint of this line joining x1 and x2. So I do expect the center of mass to be here halfway of this length, and this length is 22 centimeters. So yeah, I expect the center of mass to have its x value to be 11. Its y value is not really halfway from the x-axis to M3 because M3 is heavier than M1 and M2. So the y component of the center of mass might be a bit above the center. So let's calculate that and see. Y1 is 0, Y2 is 0. As you can see, this is because M1 and M2 are both on the x-axis. Y3 is 11, and M3 is 42, and I'll divide that by the total mass, which is 70. I got 6.6 centimeters. So the center of mass was not really at the center of the vertical line. it was actually a bit lower because the masses at the bottom are more than the masses at the top. At the bottom, I have a total mass. Let's see, does this make sense? I have the mass here 28 and 28. Yeah, so the y of the center of mass is a bit below. So I got the coordinates for the center of mass. These are parts A and B. So after discussing the center of mass, we talked a little bit about momentum, which is a quantity similar to velocity, similar to acceleration, and we associate it with objects. And it's important for the study of collisions because collisions are affected by both the mass and the velocity of the object. So the linear momentum will contain the effect of both components, the mass and the velocity. And we can calculate it. Its unit is kilograms, meter per second. And we found an important relationship between linear momentum and the net force. Basically, we just converted Newton's second law into something in terms of the linear momentum. As you can see here, I wrote the acceleration as dv by dt. And then this mass, I got it inside the derivative. I got dmv by dt, and the mv is none other but the linear momentum we defined before. So I got this relationship between Fnet and the linear momentum of a system. Namely, I got that if I have a net force acting on a system, then the linear momentum is going to be changing with respect to time. So what I'm going to discuss next is, because of what I just said, having a force will lead to a change in the linear momentum. That's what basically happens in collisions as well. In collisions, I have a brief force, a force that occurs in a very short time, but it's strong enough to slow or stop or even reverse the motion of an object. You can see in the figure here, we have a collision between the bat and the ball, or between, like you can see here, the front view. And there is basically a force acting on the ball, changing its position essentially. What we are going to define next is how we can study these collisions. Namely, we are going to look at the change of the linear momentum, and namely, we will be interested in, let's say, the speed of the ball after the collision. One thing I'm going to define is the change in the linear momentum, which I can find by Newton's second law from the force that is applied. So we said this is the formula we defined, which gives us a relationship between the net force and the change in linear momentum. I can find the change itself. Like this is a derivative, right? What if I want to find how much the change in momentum is going to be? I'll just separate for the linear momentum on one side and everything else on the other side and integrate both sides. So as you can see here, I have F is dp over dt. So I can write dp to be equal to F dt. And then I will integrate both sides. I will get the integral of dp equals the integral of F dt. I will define this left side to be the change in momentum, right? This is none other but delta P. And this, I will solve it according to what the force is in terms of time and so on. We'll have to solve that. This change in linear momentum, delta P, I will name it the impulse J. So this is a measure of how the force is integrated over time during a certain collision. This impulse of collision J is none other but the change in linear momentum, by the way. So it's equal to delta P, and by Newton's second law, J will be equal to the integral of F dt as well. So you can solve it using either method. If you have velocities before and after collision, you can find the impulse J using delta P. So I will use this if given speed before and after. I'll use this formula if given force as function of time. And then I will integrate to deduce the impulse J. So this is our first quantity which we are gonna be using to study collisions. We will find the impulse or the change in the momentum before and after a collision. One thing I want you to see here is that J can be found graphically from the force versus time graph. If you plot F versus T, remember the area is equal to whatever is on the y-axis times whatever is on the x-axis. Here, what do we have on the y-axis? F. What do we have on the x-axis? T. F times T, see from the previous slide, F times T is none other but the impulse J. This is the impulse. So I can look at the area. Now here my graph is not very helpful to find the area, but in certain cases I can have, let's say, the average force acting versus time, then the area is easier to find. I can calculate that and say this is the impulse J. Let's take a look at an example. So the figure shows an overhead view of the path taken by a race car driver as his car collides with the racetrack wall. Just before the collision, he is traveling at a speed 70 meters per second along a straight line at 30 degrees from the wall. So this is the motion before the collision. V is 70 meters per second. This is V initial. Just after the collision, he is traveling at a speed Vf equals meters per second along a straight line at 10 degrees from the wall. So this is V final, and it's equal to 50 meters per second. His mass is 80 kilograms. What is the impulse J on the driver due to the collision? Very easy. I'll just calculate the impulse J. So I'm gonna use the formula J equals delta P because I have the speeds before and after, right? Now, I want you to be aware of something. Here, the impulse J is a vector. So when I want to study vectors, I will have to project before I can add up the speeds. Like here, I'm going to write P final minus P initial, correct, but this is still a vector. And when I substitute, I write M V final minus M V initial. These are still vectors, and let's take a look at our vectors. One looks like this, the other looks like this. When you want to find their difference, you want to subtract them. This is V initial, this is V final. To subtract them, you'll have to project along X and Y axes. So I'm gonna have to write Jx to be equal to M V final X minus M V initial X. And I will have to find V final X and V initial X by projecting with respect to the angles. I can take the mass as a common, it is 80 into V final along the x-axis. Let's take a look at it. This is V final. I'll draw the x-axis just to see it and see the angle that V final makes. The wall happens to coincide with the x-axis. That's useful. V final makes this angle, which I'm told is, well, the angle is 10 degrees from the wall. This is 10. So I can directly multiply by cosine of 10. So here I'll put V final cosine 10 minus, let's look at V initial. For V initial, pay attention, my vector should start from the origin when I measure angles. So I'm gonna move V initial just with the same direction, same angle, so that it starts from the origin. Pretty up a little bit. So this is V initial. I moved it so that it starts from the origin. And now let's look at the angle. Our angle is this. The angle I was given was this one. This is given to be 30. Well, this is equal to this one because they are alternate interior angles, so it's okay. I'll just write V initial cosine 30 here. The rest is just calculation. So I'll put 80 into 50 cosine 10 minus 70 cosine 30. And now I'll do the calculations. You will get minus 910 kilograms meters per second. This is the x component of j. I need to do the same thing for the y component. This will be m into v final y minus v initial y. And for the y components, things are now easier. I'll just write v final sine of 10. One thing I wanted to notice, v final has a negative y component, so I'll plug a minus here. And v initial is, well, its y component is positive, as you can see here, so I'll just put a plus, but it has a minus already because it's a minus here. So this is going to be 70 sine 30, and v final is 50. I can substitute that. I can calculate the impulse. It will be minus 3,500 kilograms meters per second. Now, the question said, what is the impulse j? To represent your final answer, you can either write j to be equal to minus 910I minus 3,500j, or you can find the magnitude by doing radical jx squared plus jy squared. If you calculate that, let's see, you will get 3,600 kilograms meters per second. But then with this, you will have to find the angle theta. Up to you, really. You can either stop here or represent j by this method.
Professor,
Yes.
ليه عملنا هيدي الفيكتور ال V initial مع الانجل 30 بكوادرنت 1؟ ما فهمت من وين جبناها.
So you are given v initial to be like this. Can you see the vector here?
لا where؟
See the vector? Yeah.
yes,
It's
yes.
drawn for you, all right?
Yes.
Now, to find its angle with the x-axis, I move the vector so it starts from the origin. لأن أنا usually الفector بيكون هيك. كيف بجيب الانجل that it makes? I draw the x-axis. I draw it by myself, right? And I
بس
find
مش
this.
Professor هي already 30 مع negative x-axis.
لا, I don't measure the head of the arrow. I need to measure the tail of the arrow, okay, such that it's at the origin. I move the arrow so that its tail is at the origin.
Okay.
Okay, so we found the impulse J in this part. I have another part. The collision lasts for 14 milliseconds. What is the magnitude of the average force on the driver during the collision? So here I'm gonna use my second formula for the collision, which is J is equal to the integral of F dt. Now I can rearrange this formula. F average will be equal to J over the total time. And I found J previously. So here I'm gonna really need the magnitude form of J. So if I didn't find it, if I stopped here before, I'm gonna have to find that magnitude to calculate the average force. So I found the magnitude, it was 3,600. I'm gonna substitute that here. And the duration is 14 milliseconds. Notice how usually collision durations are very short. So expect like small time magnitudes. I'll calculate these. You will get 260,000. This is the force. Notice how this force is really huge, because at the end of the day, it's moving a whole car, right? Okay, these are similar questions. I will skip them. We talked also last time about conservation of linear momentum. We said if there's no net force acting on a system of particles, the total linear momentum P of the system cannot change. Where did this come from? Simply from our Newton's second law formula. F net is dP by dt. If F net is 0, then dp by dt equals 0, which means that p is constant, the linear momentum is conserved. So this conservation law is going to be at the heart of solving any problem on collisions. You can see here I have an example where I'm going to be solving essentially a collision problem without even discussing types of collisions yet. And we are going to see how we can make use of the conservation of linear momentum to solve this question. So what do we have here? Two carts in a physics lab, they roll on a level track with negligible friction. These carts have small magnets at their ends so that when they collide, they stick together. The first cart has a mass of 675 grams. It's rolling at 0.75 meters per second to the right. Let's say this is our first cart then, M1, and it was coming with V1 initial equal to 0.75 and its mass is 675 grams. M2 is 500 grams and is rolling at 1.33 meters per second also to the right. So M2 was moving to the right as well. Okay, which means this should be M2. For the two systems to collide, this should be M2 because it's going faster. So it's as if it's following the first cart and then it hits it. This is M2. M2 is faster than M1. It's as if it's following it, and at some point it really hits it. After the collision, what is the velocity of the two joined carts? So we want V final. Now, one thing is, two carts are joined after collision. So they become one object. Of mass M1 plus M2 and speed V final, which means I will not put in my formula V1 final and V2 final. Both of these are one object now. So the rest is really easy. I'm going to work with the conservation of linear momentum. I'll put P initial equals P final. This is the law of conservation because P is constant. Why is P constant? I have negligible friction, so nothing along the x-axis. There are no forces acting on the cart on the x-axis. So F net is 0, and thus the linear momentum is conserved. Initially, I have the linear momentum of the first cart times its initial speed plus the linear momentum of the second cart, which is M2 times its initial speed. And after the collision, I have both acting as one object. I will rearrange for V final. This is going to be M1 V1 initial plus M2 V2 initial over the total mass. M1 is going to be 675 times V1 initial, which is 0.75, plus M2, which is 500 times 1.33. I will divide that by 675 plus 500. I want you to notice something. Remember, these are vectors. I would have to put x and y components, except that everything here is horizontal. Otherwise, if there were any oblique velocities, I would have to project and add quantities along the x-axis, then along the y-axis. But here everything is horizontal, which makes things easier. I also need to be aware if there are any velocities to the left, I'll put these as negative. So I'm just gonna calculate this. I got 0.99 meters per second. This is the speed after the collision. So now I'm gonna look more into the study of collisions and take a look at different scenarios which occur in collisions and different conservation laws in addition to the conservation of linear momentum that we just talked about. So we defined the linear momentum, said it's m times v. It's a quantity that tells us how motion changes when objects interact, namely collide. Velocity is not enough here. The mass is also a factor. So for example, if I have a truck moving at 10 meters per second, this is harder to stop than just a tennis ball that is moving at 10 meters per second. You can see the impact of the mass, how big that is. So momentum combines the two effects, the velocity and the mass, and tells us how hard it is to stop or change an object's motion. So we're gonna use the concept of linear momentum to study collisions. And a collision is usually defined as an event during which momentum and energy are being transferred from one object to the other. So let's take a look at our systems. One thing I want you to notice is we'll have different scenarios occurring. I have this force that is being exerted during the collisions. Usually, forces cause a change in motion, right? They would accelerate an object or stop an object. Something in the motion has to change. But sometimes something else happens, which is, so if I have a force, I would have a change in the motion. If I have a net force, namely. But there's something else that we never talked about in this course, which is deformation of objects. You exert a force, sometimes it doesn't just move an object, it can deform an object. And this is something that we see a lot in collisions. Namely, in collisions, look at the different scenarios I can have. One car can push the other without a deformation, such as the here. So the bigger car just pushed the other one to the front, no change in the shape. Whereas here, you can see how this car got a bit deformed. So there's a deformation involved. What's the difference, physically speaking, between these two scenarios? I will name the first one an elastic collision. In an elastic collision, no deformation happens. And if there's no deformation, of the object, then I will say the kinetic energy is conserved. So the initial kinetic energy of both objects will be the same after the collision. If I have deformation, some energy will be lost to make this deformation. So the initial energy of the system, part of it will be lost. I will name this an inelastic collision. So we can distinguish between some types of collisions. The elastic collision, this is my first figure. Here, both momentum and kinetic energy are conserved, which is nice. I'll write P1 initial plus P2 initial equals P1 final plus P2 final. And I will write K1 initial plus K2 initial equals K1 final plus K2 final. Now, if I have a deformation, kinetic energy is not conserved. Some of the kinetic energy is converted into other types of energy, such as heat, sound, work, to permanently deform an object. So here I will only write P1 initial plus P2 initial equals P1 final plus P2 final. This is the only equation I can use. And finally, I have one more special case, which is a completely inelastic collision. This is the case when two objects stick together after the collision. So the objects stick together. Here, not all of the kinetic energy is necessarily lost, but the kinetic energy is not conserved. Some of the kinetic energy is used to stick the two objects together. So again, I will only use P1 initial plus P2 initial equals, well, What's nice about this particular case, the completely inelastic collision, is I will write P final as one object. I don't have two objects. The two objects stick together, they act as one object. This is the case that I studied in this example. Here, I actually studied a completely inelastic collision. I never told you about that because, well, the math worked without having to worry about what kind of collision I had, and I never need to study conservation of energy and see whether it's conserved or not. If you look at the three cases here, the differences between them are that one has conservation of energy, the other do not, right? So in the first figure, I can make use of this equation in case if I have multiple unknowns, then I would have two equations that I can use. So let's check an example of elastic collisions in one dimensions. So we said when we have an elastic collision, for an elastic collision, we have conservation of both linear momentum and kinetic energy, right? So the kinetic energy, the total kinetic energy of the system does not change. So I can write K1 initial plus K2 initial equals K1 final plus K2 final. And the linear momentum is conserved in this case as well. So I'll have a second equation, P1 final here, plus P2 final. So let's say I have these two spheres, M1, I'll give you some numerical values. M1 has a mass 100 grams, and it is moving at an initial speed, V1 initial equals 2 meters per second. M2 was initially at rest. Let's say M2 is 100 grams as well. This will make my question much easier. The masses can cancel out from both sides. And V2 initial is 0. I want to study how what the speeds will be after the collision. I want you to see how if I study only the linear momentum, this is not going to be enough to solve the problem. Why? Namely here, I will have M1 V1 initial plus 0 because initially V2 was at rest. This is equal to M1 V1 final plus M2 V2 final. Now the masses cancel out because they are all the same. V1 initial is 2. But I don't know V1 final and I don't know V2 final. What I want is both of these, right? So what I'm going to do essentially is I'm going to make use of the conservation of kinetic energy. I want you to see how the conservation equations will look like. Namely, this is the linear momentum conservation, and I will apply conservation of kinetic energy, which will look like this. Now here, the slide combines the two equations and gives you a general formula, but what I like to do is I wrote for the first equation, I substituted the values. I got 2 equals V1 final plus V2 final. This is the linear momentum conservation law. For the kinetic energy, in our case, I have half M1 V1 initial squared equals half M1 V1 final squared plus half M2 V2 final squared. The masses cancel out because I took a particular case where the masses are the same. The halves cancel out. V1 squared will be 4, and this is V1 squared plus V2 final squared. This is the second equation I got. I have these two equations. What I will do is that I will simply substitute V1 final to be 2 minus V2 final. And then I will solve the system of two equations to unknowns. So I will get here 4 equals 2 minus V2 final squared plus V2 final squared. And you can solve for V2 final and then deduce V1 final from here. That's a very typical collisions question. You can see here also I have some other examples. Namely, I have a general case, didn't do any conservation of energy yet. If I have a completely inelastic collision, the two masses will combine into one mass. So things will look like this. If the first mass is at rest, then I'll have m1 v1 initial plus 0 equals m1 plus m2 times v. Both masses combine into one mass. This is the conservation of linear momentum. And then it will look like this, and I can solve for the final speed. I'll just rearrange as we did in the question of the two carts that combined into one. One typical example of a completely inelastic collision is this, what we name a ballistic pendulum. In a ballistic pendulum, you shoot an arrow or an object towards a pendulum, and then when the arrow hits the pendulum, it lifts it a little bit. So here, the pendulum has an initial speed 0. The arrow has some larger initial speed, and after the collision, the two objects stick together. So this is a completely inelastic collision. So I can use m1 v1 plus 0 equals m1 plus m2 v. And I can solve for the speed after the collision. Very easy.